So we're now going to see the effects of the different factors that affect the rate of a reaction. The first factor that we'll see is the effect of concentration. So at low concentrations, we're going to have few particles per unit volume. And if we have few particles, we're going to have few collisions, and fewer collisions mean less effective collisions. So less effective collisions means a slow reaction. As concentration increases, we're going to have more particles per unit volume, and more particles per unit volume mean more collisions, which imply more effective collisions, more successful collisions. Therefore, rate of reaction is faster. Now, when we have a reaction that proceeds with time, at the beginning of the reaction, this is when you have the highest amount of the reactants, because the reaction has just started. You have 100% of the reactants, so concentration is maximum. As the reaction proceeds, you have more and more reactants that get converted to products. But as the reaction proceeds, you have less amounts of reactants, so that at time zero, the concentration of reactants is maximum. So the rate of reaction is going to be maximum. You have maximum effective collisions. At the end of the reaction, you have the minimum concentration of the reactants, because most of the reactants have been converted to products. So at this point, you have minimum rate of reaction because you have minimum collisions. So for any reaction, the rate of the reaction decreases with time as the concentration of the reactants decrease. The second factor that we'll see is pressure. Now, pressure is almost similar as concentration. However, pressure relates to only those reactions that involve gaseous reactants. Only when the reactants are gaseous that we can talk about the effect of pressure on the rate of reaction. And if a reactant is a solid or a liquid, then pressure will have no effect on the rate of that reaction. When we increase the pressure of a gas, we are compressing the gas. So we have the same number of gas particles, but in a smaller volume. So this means that the particles are closer to each other. So the number of gas particles per unit volume increases, which means that the number of collisions will increase, and which eventually means that the number of successful collisions will increase. The next factor is the effect of particle size on rate of reaction. So large particles have small surface area. So as you can see here, this is a large particle of a reactant, and you can see that you have 8 particles that are able to collide with the big reactant solid particle. But when you have smaller size of the solid, as it's shown here, we can see that 20 collisions that are happening. So the smaller the size of the particles, the larger the surface area to volume ratio. Hence, the more collisions you're going to have, more collisions result in more successful collisions, and hence you have a faster reaction. So small particles of solid have large surface area to volume ratio that is exposed for the reactant particles to collide. And this effect can be demonstrated by a reaction of calcium carbonate and hydrochloric acid. So if you have small surface area of the calcium carbonate, you're going to have a very quick reaction. So if you carry out the reaction using, so in one experiment, you use marble chips. Another experiment, you use powder. You're going to see that the powder is going to react faster than the marble chips. If you have any kind of particle that's intermediate between these two, the rate of reaction will be intermediate. Now, relating to surface area, you can explain that very fine dust powders catch fire or become explosive because of the large surface area of these powders. So very large surface area of coal and flour in mills account for the fact that these areas need to be protected from any form of ignition or any form of spark that could lead to an explosion because of the large surface area to volume ratio of the powder.